Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This counterintuitive concept first gained prominence in the early 20th century when Einstein, Podolsky, and Rosen presented a paradox that questioned the completeness of quantum mechanics. They suggested that if quantum mechanics were correct, it would imply spooky action at a distance which they found troubling. This led to the famous debate between Einstein and Niels Bohr, and later, John Bell's theorem, which showed that no local hidden variables could account for entanglement, thus reinforcing the strange predictions of quantum mechanics. In the realm of science, particles become entangled when they interact in such a way that their quantum states become dependent on one another. When one particle's state is measured, the state of the other particle is instantly determined, no matter how far apart they are. This process is deeply linked with the principle of superposition, where particles exist in multiple states simultaneously until measured, leading to what is known as wave function collapse. Experiments like those conducted by Elaine Aspect in the 1980s have demonstrated this entanglement, showing that the measurement of one particle affects its entangled partner, thereby providing empirical support for the theory. The concept of quantum entanglement opens fascinating possibilities for communication. Quantum communication utilizes entanglement to create secure channels, as any eavesdropping on quantum data alters the data itself, making it detectable. Unlike classical communication, which relies on transmitting signals over distances, quantum communication can theoretically transmit information instantaneously across vast distances due to entanglement. Quantum teleportation, often depicted in science fiction, involves transferring quantum states from one particle to another without physically moving the particle itself. Unlike its fictional counterparts, real quantum teleportation does not transport matter, but rather transmits information, leveraging entanglement to reconstruct quantum states at a distant location. Space communication presents significant challenges due to signal delay and data loss over long distances. The vast expanses between celestial bodies mean that signals take time to travel, complicating real-time communication and data transfer. Quantum entanglement could potentially overcome these hurdles by offering instantaneous information exchange, though practical implementation remains complex. Recent advancements include quantum satellites, such as China's Miseus satellite, which has demonstrated quantum communication from space. Miseus has enabled secure quantum key distribution and tested entanglement over thousands of kilometers, marking a significant step forward in space-based quantum experiments. These experiments provide proof of concept for the feasibility of using quantum entanglement in space communication, though many hurdles remain. The potential applications of quantum entanglement are immense. Quantum key distribution (QKD) promises ultra-secure communication channels, as any interception would be immediately apparent. Furthermore, the enhancement of deep space communication networks could improve data transmission between Earth and distant space missions, making it feasible to support advanced space exploration and future colonization efforts. Technologically, maintaining entanglement over long distances poses considerable difficulties. Quantum states are susceptible to decoherence, where environmental factors disrupt the delicate quantum states. Researchers are working on solutions to mitigate these issues, such as developing better quantum error correction techniques and creating more robust quantum systems. Ethically and philosophically, the rise of quantum communication raises questions about privacy and security. The potential for unbreakable encryption could shift how we handle sensitive information, while philosophical discussions about the nature of reality and information transfer are sparked by the non-local nature of entanglement. Looking ahead, ongoing research is exploring new frontiers in quantum communication. Future projects aim to refine quantum technologies and overcome current limitations. With rapid advancements, the next decade could see significant breakthroughs that could revolutionize how we communicate across space and fundamentally alter our understanding of the universe. It is a phenomenon in quantum mechanics where the quantum states of two or more particles become interconnected, such that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This intricate and perplexing connection defies classical intuitions and suggests a deep, mysterious bond between entangled particles, where measuring one particle's state instantaneously determines the state of its partner. This defies our classical understanding of locality, where objects are only directly influenced by their immediate surroundings. The concept of quantum entanglement emerged from the fertile intellectual ground of the early 20th century, a time when the very foundations of physics were being questioned and reimagined. The seeds of this revolutionary idea were sown in the minds of pioneering scientists like Albert Einstein, Boris Podolsky, and Nathan Rosen. In 1935, these three physicists presented a thought experiment that came to be known as the Einstein-Podolsky-Rosen (EPR) paradox. This paradox questioned the completeness of quantum mechanics, positing that if the theory were complete, it would imply spooky action at a distance, where changes in one particle could instantaneously affect another, no matter how far apart they were. The EPR paradox was a challenge to the Copenhagen interpretation of quantum mechanics, which posited that particles do not have definite properties until they are measured. Einstein, in particular, was deeply troubled by the implications of quantum entanglement. To him, the idea of instantaneous action at a distance seemed to violate the principle of locality, a cornerstone of his theory of relativity. Einstein famously referred to this phenomenon as spooky action at a distance, a term that has since become synonymous with the mysterious nature of quantum entanglement. Despite his reservations, Einstein's work on the EPR paradox inadvertently laid the groundwork for future explorations into the depths of quantum mechanics. The conceptual landscape of quantum entanglement continued to evolve over the following decades, with physicists grappling with the implications of the EPR paradox and the nature of quantum reality. In the 1960s, the Irish physicist John Bell provided a crucial breakthrough with his formulation of Bell's theorem. Bell's theorem demonstrated that no local hidden variable theories could reproduce all the predictions of quantum mechanics. This theorem provided a way to test the validity of quantum entanglement through experimental means, offering a concrete framework for examining the enigmatic connections between entangled particles. The story of quantum entanglement took an unexpected turn in the 1980s, with a series of groundbreaking experiments conducted by physicists Elaine Aspect, John Clauser, and Anton Zeilinger, among others. These experiments provided compelling evidence supporting the predictions of quantum mechanics and confirming the existence of quantum entanglement. Using sophisticated techniques to measure the correlations between entangled particles, these experiments demonstrated that the results were consistent with the non-local nature of entanglement, violating the inequalities derived from Bell's theorem. The findings of these experiments were nothing short of revolutionary, solidifying the status of quantum entanglement as a fundamental aspect of the quantum world. As our understanding of quantum entanglement deepened, so too did our appreciation for its potential applications. The bizarre properties of entanglement opened the door to a host of groundbreaking technologies, including quantum computing and quantum cryptography. In a quantum computer, entangled qubits can process vast amounts of information simultaneously, potentially revolutionizing fields ranging from cryptography to complex simulations. Quantum cryptography leverages the principles of entanglement to create theoretically unbreakable communication channels, ensuring the utmost security in transmitting sensitive information. Beyond its technological implications, quantum entanglement also invites us to reconsider our understanding of reality itself. The interconnectedness of entangled particles suggests that the universe is fundamentally holistic, with all parts deeply intertwined in ways that defy classical logic. This perspective echoes ancient philosophical and spiritual traditions that have long posited a profound interconnectedness underlying the fabric of existence. Imagine, if you will, a distant future where the mysteries of quantum entanglement have been fully harnessed and integrated into everyday life. In this hypothetical world, communication across vast cosmic distances becomes instantaneous, transcending the limitations of the speed of light. A message sent from Earth to a colony on a distant exoplanet is received in the blink of an eye, thanks to the entangled quantum states of particles in advanced communication devices. The implications of such technology are profound, reshaping our understanding of space and time, and fostering a sense of unity among civilizations spread across the cosmos. In this imagined future, quantum entanglement also transforms the field of medicine. Advanced diagnostic devices utilize entangled particles to scan and analyze the human body with unprecedented precision, detecting ailments at their earliest stages and enabling treatments that are both highly effective and minimally invasive. The interconnectedness of entangled particles also inspires new approaches to holistic healthcare, emphasizing the importance of treating the body, mind, and spirit as an interconnected whole. Even the realm of art and creativity is revolutionized by quantum entanglement. Artists and musicians experiment with entangled particles to create immersive, multi-sensory experiences that transcend traditional boundaries. Entangled states enable artists to collaborate instantaneously across great distances, blending their unique perspectives into harmonious works of art that resonate on a profound, almost mystical level. Yet, amid these fantastical advancements, the philosophical and ethical implications of quantum entanglement continue to spark lively debate. The non-local nature of entanglement challenges our traditional notions of causality and free will, raising questions about the very nature of human agency. Are our actions truly independent, or are they subtly influenced by the entangled states of particles that connect us to the broader universe? These questions invite us to explore the profound interconnectedness of all things and to consider the ways in which our individual choices reverberate through the intricate web of existence. As we navigate the complexities of this quantum future, we are reminded of the humble origins of quantum entanglement in the minds of visionary scientists like Einstein, Podolsky, Rosen, and Bell. Their pioneering work laid the foundation for a new understanding of the universe, one that continues to unfold in surprising and wondrous ways. The journey of quantum entanglement is a testament to the power of human curiosity and the boundless potential of scientific inquiry, inviting us to explore the mysteries of the quantum realm and to embrace the profound interconnectedness that binds us all. Quantum entanglement is one of the most intriguing and mysterious phenomena in the realm of quantum mechanics, a theory that governs the behavior of the smallest particles in the universe. The concept of entanglement suggests that particles, once linked, remain connected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection defies classical notions of locality and causality, painting a picture of the universe where distance is an illusion and information transfer can occur faster than the speed of light. To understand how particles become entangled, we must first delve into the enigmatic world of quantum mechanics. When two particles interact in certain ways, their individual quantum states merge into a single, entangled state. This means their properties, such as spin, position, and momentum, become intertwined. For instance, if two electrons are entangled, measuring the spin of one electron will instantly determine the spin of the other, even if they are separated by galaxies. This instantaneous correlation persists regardless of the distance separating them, suggesting a profound interconnectedness in the fabric of reality. The principle of superposition plays a crucial role in quantum entanglement. In the quantum world, particles do not reside in a single state, but rather exist in a superposition of all possible states until measured. For example, an electron in superposition can simultaneously spin both up and down. This is analogous to Schrödinger's famous thought experiment, where a cat in a box can be both alive and dead until someone opens the box and observes it. When particles are entangled, their superpositions become linked, creating a complex, intertwined quantum state. This means that the superposition of one particle's state is dependent on the state of its entangled partner. Wave function collapse is another fundamental concept intertwined with superposition and entanglement. The wave function represents the probability distribution of a particle's possible states. When an observation or measurement is made, the wave function collapses, and the particle assumes a definite state. In the case of entangled particles, measuring one particle's state causes the wave function of the entire entangled system to collapse, instantaneously determining the state of the other particle. This collapse occurs faster than the speed of light, challenging Einstein's theory of relativity and the notion that nothing can travel faster than light. Einstein famously referred to this phenomenon as spooky action at a distance. One of the most famous and convincing demonstrations of quantum entanglement came from the experiments conducted by Alain Aspect and his team in the 1980s. Aspect's experiments aimed to test the validity of Bell's theorem, which posits that no local hidden variable theory can reproduce all the predictions of quantum mechanics. Hidden variable theories suggest that particles have predetermined properties that determine their states, thus preserving classical notions of locality and realism. However, Bell's theorem implies that if quantum mechanics is correct, these hidden variable theories must be non-local, meaning they allow for faster-than-light interactions. Aspect's experiments involved creating pairs of entangled photons and sending them to different locations where their polarizations were measured. The results showed correlations between the polarizations that could not be explained by any local hidden variable theory. The measurements of one photon's polarization were found to influence the polarization of the other photon instantaneously, regardless of the distance separating them. This confirmed that quantum entanglement was real and that the universe operated in a fundamentally non-local manner. The implications of quantum entanglement extend beyond mere scientific curiosity. They challenge our understanding of reality and hint at a deeper, more interconnected universe. Some physicists have speculated that entanglement could be harnessed for revolutionary technologies, such as quantum computing and quantum communication. Quantum computers, for instance, could perform complex calculations exponentially faster than classical computers by exploiting entanglement and superposition. Quantum communication, on the other hand, could enable perfectly secure communication channels, as any attempt to eavesdrop on the entangled particles would disrupt their state and be immediately detectable. In the realm of fiction, the possibilities of quantum entanglement are even more tantalizing. Imagine a future where humans can use entanglement to communicate instantaneously across vast cosmic distances. Spaceships could navigate the stars with perfect precision, using entangled particles to stay connected to mission control back on Earth. Explorers could share their experiences in real time, creating a network of consciousness that spans the galaxy. Even more fantastically, some have imagined using entanglement to achieve teleportation, disassembling particles at one location and reassembling them at another instantaneously. While these ideas remain firmly in the realm of science fiction, they underscore the profound impact that understanding and harnessing entanglement could have on our civilization. Yet, for all its promise and mystery, quantum entanglement remains deeply puzzling. It forces us to reconsider our assumptions about the nature of reality, locality, and causality. How can particles separated by light years remain connected? What does this mean for our understanding of space and time? These questions continue to drive physicists to explore the quantum world, seeking to unravel its secrets and perhaps unlock new dimensions of understanding. In some speculative scenarios, entanglement might even provide insights into the fundamental structure of the universe. Some theories suggest that the universe itself could be a vast interconnected web of entangled particles, with every particle influencing every other particle across the cosmos. This vision aligns with the holistic views found in some philosophical and mystical traditions, which see the universe as a unified whole where everything is interconnected. The journey to fully comprehend quantum entanglement is far from over. Each experiment and theoretical advance brings us closer to understanding this profound phenomenon, but also reveals new layers of complexity and mystery. As we continue to probe the quantum realm, we may find answers to some of the most profound questions about the nature of reality itself. In the meantime, quantum entanglement remains a captivating testament to the strangeness and wonder of the universe, a reminder that there is still so much to learn and discover. So, in this vast and mysterious universe, quantum entanglement stands as a beacon of interconnectedness, a phenomenon that transcends classical boundaries and invites us to explore the deeper, hidden dimensions of reality. It challenges our perceptions, fuels our imaginations, and propels us on a quest to understand the true nature of existence. Whether through rigorous scientific inquiry or flights of speculative fancy, the study of quantum entanglement promises to reshape our understanding of the cosmos and our place within it. Quantum communication represents a fascinating frontier in the realm of information exchange, rooted in the mysterious and counterintuitive principles of quantum mechanics. Unlike classical communication methods that rely on traditional means like electrical signals, optical fibers, and electromagnetic waves to transmit data, quantum communication leverages the peculiar properties of quantum states, such as superposition and entanglement, to convey information in fundamentally novel ways. At its core, quantum communication exploits the principle of superposition, where a quantum particle like a photon can exist in multiple states simultaneously. This is akin to a spinning coin being both heads and tails at once until observed. In the realm of communication, this allows for the encoding of information in qubits, which, unlike classical bits that are strictly 0 or 1, can be in a superposition of both states. This feature can potentially allow quantum communication systems to process and transmit vast amounts of information more efficiently than classical systems. Another fundamental principle at play is quantum entanglement. When two particles become entangled, their states are interlinked such that the state of one particle instantly influences the state of the other, no matter how far apart they are. This peculiar connection persists regardless of the distance separating the particles, leading to what Einstein famously referred to as spooky action at a distance. In the context of communication, entangled particles can be used to establish a secure channel where any attempt at eavesdropping would disturb the entanglement, alerting the communicating parties to the presence of an intruder. In comparison to classical communication methods, quantum communication offers several compelling advantages, particularly in the domain of security. Classical communication channels, such as the internet, are susceptible to interception and hacking. Information transmitted over these channels can be copied and accessed without the sender or receiver being aware of the breach. Quantum communication, on the other hand, can theoretically offer perfect security through a protocol known as quantum key distribution (QKD). In QKD, a cryptographic key is shared between two parties using entangled particles. Any attempt to eavesdrop on the key will inevitably disturb the quantum states, thereby revealing the presence of an interceptor and ensuring the integrity of the communication. One of the most intriguing and widely discussed concepts in quantum communication is quantum teleportation. Contrary to the teleportation depicted in science fiction, where objects or people are instantaneously transported from one place to another, quantum teleportation involves the transfer of quantum information from one particle to another, effectively teleporting the state of a particle. This process relies heavily on entanglement. When a particle, such as a photon, is entangled with another particle, the quantum state of the first particle can be transferred to the second particle, even if they are separated by vast distances. This transfer is accomplished without moving the particle itself, but rather by transmitting the quantum information about the particle's state. To understand quantum teleportation more clearly, consider a fictional scenario in a futuristic setting, where quantum communication networks are as commonplace as today's internet. In this world, scientists have developed a quantum teleportation device that allows for instantaneous transmission of information between planets. On Earth, a scientist named Dr. Elena decides to send a quantum message to her colleague, Dr. Aiden, stationed on a distant space station orbiting Jupiter. Using their entangled particles, Dr. Elena encodes her message onto a photon and performs a series of quantum operations, effectively entangling the message with the photon's state. Dr. Aiden, equipped with his quantum receiver, observes the entangled state, and the message appears instantaneously in his system, even though the actual particle carrying the message has never physically traveled the immense distance between Earth and Jupiter. This fictional portrayal, while simplified, captures the essence of quantum teleportation. It is important to note, however, that actual quantum teleportation cannot transport matter or energy, but only information about the quantum state of a particle. This distinction sets it apart from the teleportation seen in science fiction, which often involves the physical movement of objects or beings across space. The implications of quantum communication extend far beyond secure messaging. In the realm of computing, quantum networks could connect quantum computers, enabling them to work together to solve complex problems that are currently intractable for classical computers. Quantum communication could revolutionize fields such as cryptography, where the ability to generate and distribute truly random keys ensures unbreakable encryption, and in the development of new technologies like quantum internet, which promises unprecedented speeds and security. Yet, the journey towards realizing the full potential of quantum communication is fraught with challenges. One major hurdle is the fragility of quantum states. Quantum particles are extremely sensitive to their environment, and any interaction with external factors can cause decoherence, disrupting the superposition and entanglement that quantum communication relies on. This makes it difficult to maintain quantum states over long distances and through various media. In the near future, advances in quantum repeaters devices that can amplify and retransmit quantum signals without disturbing their quantum states are expected to mitigate some of these challenges. Moreover, the development of error correction techniques tailored to quantum systems will be crucial in making quantum communication more robust and reliable. Despite these challenges, the prospects of quantum communication continue to inspire both scientists and the general public. Envision a world where financial transactions are conducted with absolute security, where confidential information is exchanged with the certainty that it cannot be intercepted, and where quantum networks enable the seamless collaboration of quantum computers across the globe. Such a world, once the stuff of science fiction, is gradually becoming a tangible reality as researchers unlock the secrets of the quantum realm. In conclusion, quantum communication represents a paradigm shift in how we understand and implement information exchange. It harnesses the strange and wondrous principles of quantum mechanics to offer unparalleled security and efficiency, distinguishing itself markedly from classical communication methods. The concept of quantum teleportation, while often conflated with its science fiction counterpart, underscores the profound differences between quantum and classical paradigms. As research progresses and technology evolves, the implications of quantum communication will undoubtedly reshape our digital landscape, heralding an era of unprecedented advancements in secure and efficient information transfer. In the vast expanse of space, communication is both a marvel and a challenge. As humanity extends its reach beyond our blue planet, the need to communicate efficiently and reliably with spacecraft, satellites, and potential colonies becomes increasingly vital. Yet, the methods we currently employ to transmit information through the void are fraught with issues that complicate our endeavors. Signal delay, data loss, and the sheer vastness of space present formidable barriers. The vast distances involved in space communication lead to significant signal delays. When we send a command to a rover on Mars, for instance, it can take anywhere from 4 to 24 minutes for the signal to travel, depending on the relative positions of Earth and Mars. This latency hampers real-time communication and makes immediate responses impossible. Imagine an astronaut on a distant moon, urgently needing assistance, having to wait minutes or even hours for a response from Earth. Such delays can be critical, even life-threatening. Data loss is another significant issue. Space is not a benign environment for electromagnetic waves. Solar flares, cosmic radiation, and even the interstellar medium can distort or attenuate signals. This interference can cause data packets to be lost or corrupted, necessitating retransmissions and leading to further delays. The deep space missions, like those undertaken by Voyager probes, often suffer from weak signals that degrade over time as the distance from Earth increases. The farther a spacecraft travels, the more tenuous our communication link becomes. Bandwidth limitations also pose challenges. The amount of data we can send and receive is restricted by the available spectrum and the power of our transmission systems. This limitation becomes more pronounced as we explore farther into the solar system and beyond. High-resolution images, complex scientific data, and real-time video feeds require substantial bandwidth, which is not always available or feasible for deep space missions. In light of these challenges, the idea of using quantum entanglement for space communication has garnered significant interest. Quantum entanglement, a phenomenon where particles become interlinked such that the state of one instantly influences the state of another, regardless of distance, offers the tantalizing prospect of instantaneous communication. Imagine a scenario where an astronaut on Mars could instantly communicate with mission control on Earth without any delay. This could revolutionize space exploration, making real-time decision-making and immediate responses possible. In a not-so-distant future, let's envision a mission to a distant exoplanet orbiting a star many light-years away. Aboard the spacecraft, equipped with advanced quantum communication systems, astronauts embark on a journey that will take decades to complete. These systems use pairs of entangled particles distributed between Earth and the spacecraft before launch. As the spacecraft ventures into the unknown, the entangled particles ensure that any change in the state of a particle on the spacecraft is instantaneously reflected in its twin particle on Earth. Back on Earth, mission control monitors the journey, receiving data without the crippling delays that have plagued previous missions. The instantaneous communication allows the team to assist the astronauts in real time, whether it's troubleshooting equipment, providing medical advice, or even offering moral support. The spacecraft encounters an unexpected asteroid field, and the crew needs to perform evasive maneuvers. Thanks to quantum communication, they receive immediate guidance from Earth, avoiding disaster. As the mission progresses, the astronauts send back high-definition images and complex data about the exoplanet's atmosphere, surface, and potential for life. The quantum communication system handles the data effortlessly, without the bandwidth constraints of traditional radio signals. Scientists on Earth analyze the information in real time, making discoveries that would have been impossible with the delays of conventional communication methods. The journey to the exoplanet takes the crew through regions of space with high levels of cosmic radiation. Traditional communication systems might have struggled with data corruption in such an environment, but quantum entanglement proves resilient. The entangled particles remain unaffected by the harsh conditions, ensuring a reliable communication link. The crew feels a profound sense of connection to Earth, knowing that their every word and action is being received instantaneously by mission control. This psychological boost is invaluable, as the isolation of space can take a toll on even the most resilient individuals. As the spacecraft nears its destination, the crew prepares to land on the exoplanet. They transmit critical data about the landing site, including topographical maps and atmospheric readings. Mission Control, armed with this real-time information, guides the crew to a safe landing. The quantum communication system proves its worth once again, enabling a smooth and successful touchdown on the alien world. The exploration of the exoplanet begins, and the crew encounters strange and wondrous phenomena. They send back real-time video feeds of alien landscapes, bizarre life forms, and potential resources. The scientists on Earth, watching in awe, provide immediate feedback and suggestions for further investigation. The synergy between the crew and mission control leads to groundbreaking discoveries that reshape our understanding of the universe. One day, while exploring a particularly intriguing region of the exoplanet, the crew discovers signs of an ancient civilization. They transmit detailed images and data back to Earth, sparking a flurry of excitement and activity among archaeologists, historians, and scientists. The quantum communication system handles the massive influx of data with ease, allowing for a collaborative effort that spans the vast distance between the exoplanet and Earth. The crew uncovers artifacts and structures that reveal the civilization's history, culture, and eventual decline. This discovery has profound implications for humanity, offering insights into the potential future of our own civilization. The mission eventually concludes, and the crew prepares for the long journey back to Earth. Throughout the return voyage, the quantum communication system continues to provide instantaneous contact with mission control. The crew feels a deep sense of accomplishment, knowing that their efforts have expanded the frontiers of human knowledge. They return to Earth as heroes, having demonstrated the incredible potential of quantum communication in overcoming the challenges of space exploration. The success of the mission to the exoplanet marks the beginning of a new era in space communication. Quantum entanglement becomes the standard for all future missions, enabling humanity to explore the farthest reaches of the cosmos with unprecedented ease. The dream of interstellar travel, once hindered by the limitations of conventional communication methods, becomes a reality. The universe opens up to us, and we venture forth with confidence, knowing that the vast distances of space are no longer an insurmountable barrier. As we stand on the cusp of this new frontier, we realize that the challenges of space communication are not just technical obstacles to be overcome, but opportunities for innovation and discovery. Quantum entanglement, with its promise of instantaneous communication, represents a paradigm shift that will transform our approach to space exploration. The future is bright, and the stars are within our reach. Quantum satellites represent the cutting edge of communication technology, pushing the boundaries of what we thought possible in the realm of secure data transmission. The advancements in this field are fascinating, particularly the efforts led by China with its Milestones satellite. Named after the ancient Chinese philosopher and scientist, Milestones, also known as Mozi, the satellite was launched in August 2016 as part of the Quantum Experiments at Space Scale (QUES) project. It was designed to explore the feasibility of quantum communication over long distances, something that had only been theorized and tested over relatively short distances on Earth. Quantum communication leverages the principles of quantum mechanics, particularly quantum entanglement, to enable a new level of security and speed. Quantum entanglement is a phenomenon where two particles become linked, and the state of one instantly influences the state of the other, no matter the distance between them. This means that information could be transmitted instantly and securely, as any attempt to intercept a communication would alter the state of the particles and be immediately detectable. The Milestones satellite was a game changer. Its mission was to test quantum key distribution, QKD, a method of secure communication that uses quantum mechanics to ensure the privacy of encryption keys. Traditional encryption methods can be broken with enough computational power, but QKD theoretically provides an unbreakable encryption. In one of its groundbreaking experiments, Milestones successfully transmitted entangled photons between ground stations separated by more than 1,200 kilometers. This was a significant leap from previous ground-based experiments, which were limited by the curvature of the Earth and atmospheric interference. The success of Milestones wasn't just a technological marvel, it was also a geopolitical statement. It demonstrated China's capabilities in quantum technology, an area of strategic importance for future communications, cryptography, and even quantum computing. The international scientific community watched in awe as China set the stage for a new era of space-based quantum experiments. But the story of quantum satellites doesn't end with Milestones. Inspired by its success, researchers and engineers around the world began to pursue similar projects. The European Space Agency, for instance, initiated its own quantum satellite program, aiming to create a network of satellites capable of QKD. Meanwhile, private companies saw the commercial potential in this technology, envisioning a future where quantum satellites could secure financial transactions, protect governmental communications, and even create a global quantum internet. Amid these real-world advancements, the realm of fiction began to explore the possibilities of quantum communication in space. Imagine a future where humanity has colonized multiple planets and established vast space stations orbiting distant stars. In this world, traditional communication methods would be too slow and vulnerable to interception. Quantum satellites, on the other hand, would provide instantaneous and secure communication channels between these far-flung outposts. In this speculative future, quantum satellites are more than just communication tools. They become crucial components of interstellar governance and diplomacy. The security provided by quantum communication ensures that treaties and agreements between planetary colonies are confidential and unbreakable. Any breach in this communication could be seen as an act of war, making the maintenance of these satellites a matter of planetary security. One can imagine the daring adventures of quantum engineers tasked with maintaining and upgrading these satellites. These engineers are the unsung heroes, working in the vacuum of space, repairing and calibrating the delicate equipment that ensures the stability of the quantum network. They might encounter challenges ranging from cosmic radiation to sabotage by rogue factions, seeking to disrupt the fragile peace maintained by quantum communication. Back in our present reality, the experiments with quantum satellites continue to yield promising results. In addition to QKD, researchers are exploring other applications of quantum entanglement in space. For example, they are investigating the potential of quantum teleportation, where the state of a particle is transferred from one location to another instantaneously. While this doesn't mean teleporting matter as depicted in science fiction, it could revolutionize data transmission, making it faster and more secure than ever before. Moreover, the integration of quantum satellites with ground-based quantum networks is becoming a hot topic. Scientists are working on creating hybrid systems where quantum satellites connect with fiber optic quantum networks on the ground. This hybrid approach could bridge the gap between current technological capabilities and the dream of a global quantum internet. Despite the incredible progress, challenges remain. The technology is still in its infancy, and there are significant technical hurdles to overcome. For instance, maintaining the entanglement of photons over long distances and through the turbulent atmosphere is no easy feat. Additionally, the infrastructure required to support a global quantum network is immense and costly. But the potential rewards are too great to ignore. As we look to the future, the possibilities of quantum satellites and space-based quantum experiments seem boundless. Beyond secure communication, these advancements could pave the way for new discoveries in fundamental physics. Space provides a unique environment where the effects of gravity and other earthly influences are minimized, allowing scientists to test the principles of quantum mechanics in ways that are impossible on Earth. In a distant future, perhaps humanity will look back at the launch of Milestones as the beginning of a quantum revolution. Just as the invention of the internet transformed society in ways that were unimaginable at its inception, quantum communication could usher in a new era of connectivity and security. It's a future where information flows seamlessly and securely across the vast expanse of space, connecting civilizations and fostering a new age of exploration and understanding. The journey of quantum satellites is a testament to human ingenuity and the relentless pursuit of knowledge. From the successful experiments of Milestones to the speculative futures of interstellar quantum networks, this field embodies the spirit of exploration and the quest for deeper understanding. As we continue to push the boundaries of what is possible, the story of quantum satellites will undoubtedly be one of the most exciting chapters in the history of science and technology. In a future not so distant, the landscape of technology and space exploration began to shift dramatically with the advent of quantum communication. This revolutionary leap was driven by the potential of quantum key distribution, QKD, a method that utilized the principles of quantum mechanics to enable secure communication. Unlike classical encryption methods, QKD provided an unbreakable encryption system, ensuring that any attempt to intercept the communication would immediately alert the users. This technological marvel opened a realm of possibilities, not only for secure communication on Earth, but also for the nascent networks being developed for deep space exploration. In the year 2045, as humanity stood on the brink of becoming an interplanetary species, the necessity for robust and secure communication systems became paramount. The Moon had already seen its first permanent outpost, and Mars colonization was in its initial stages. The communication delay caused by the vast distances between Earth and these celestial bodies posed a significant challenge. However, the integration of quantum communication into space networks promised to mitigate these issues. Quantum entanglement, a phenomenon where particles become interconnected and instantly affect each other regardless of distance, became the cornerstone of this new communication paradigm. As research progressed, scientists discovered that quantum entanglement could be harnessed to create a network where data transmission was instantaneous, bypassing the limitations imposed by the speed of light. This breakthrough meant that astronauts on Mars could communicate with Earth in real time, receiving critical instructions and updates without the frustrating delays. Furthermore, the unbreakable security provided by QKD ensured that these communications were impervious to hacking attempts, which was crucial for the safety and success of space missions. The implications of these advancements extended beyond mere communication. The establishment of a quantum-based deep space network facilitated the remote operation of rovers and other robotic explorers on distant planets and moons. These machines, equipped with quantum communication modules, could send high-definition images and data back to Earth in real time. This instantaneous feedback loop allowed scientists to make quick decisions and adjustments, significantly increasing the efficiency of exploratory missions. One of the most profound impacts of quantum communication was on the concept of space colonization. As humanity began to establish colonies on Mars and other celestial bodies, the need for a reliable and secure communication infrastructure became even more critical. The colonies depended on Earth for supplies, information, and emotional support. With quantum communication, colonists could maintain a seamless connection with their families and colleagues back on Earth, reducing the psychological strain of isolation. This continuous connection was vital for the mental well-being of the pioneers venturing into the harsh environments of space. Moreover, quantum communication facilitated the development of advanced life support systems. These systems, integrated with artificial intelligence, relied on constant data streams to monitor and adjust environmental conditions within the habitats. Any malfunction or anomaly could be detected and rectified immediately, ensuring the safety of the colonists. The real-time data transmission enabled by quantum communication was a key factor in making these life support systems reliable and efficient. In a twist of fate, quantum communication also played a pivotal role in the detection and prevention of cosmic threats. As humanity ventured deeper into the cosmos, the risk of encountering unknown dangers increased. The ability to instantly share information across vast distances allowed for the early detection of potentially hazardous asteroids or other celestial phenomena. Advanced warning systems, powered by quantum networks, could alert both Earth and space colonies, enabling timely evasive actions or countermeasures. The story of humanity's expansion into space was not without its challenges. The initial stages of implementing quantum communication networks were fraught with technical difficulties and skepticism. Critics argued that the technology was still in its infancy and that the reliance on quantum principles was a gamble. However, a dedicated team of scientists and engineers, driven by a vision of a connected and secure interplanetary society, persevered. Through relentless experimentation and innovation, they overcame the obstacles, gradually transforming the skeptics into believers. By the year 2060, quantum communication had become the backbone of interplanetary networks. Space stations, lunar outposts, and Martian colonies were all interconnected through this advanced technology. The once fragmented and isolated human presence in space had evolved into a cohesive and coordinated effort. The seamless flow of information enabled by quantum communication allowed for collaborative research and development, accelerating scientific discoveries and technological advancements. Among the many applications of quantum communication, one particularly fascinating area was the field of space medicine. The harsh environment of space posed numerous health risks to astronauts and colonists. Quantum communication allowed for the real-time monitoring of vital signs and the remote diagnosis of medical conditions. Medical experts on Earth could consult with doctors in space, providing guidance and support for complex medical procedures. This capability was crucial in emergencies, where timely intervention could mean the difference between life and death. The impact of quantum communication on space exploration was not limited to the human presence in the solar system. As robotic explorers ventured further into the unknown, quantum communication enabled the transmission of vast amounts of data from distant celestial bodies. Missions to the outer planets, their moons, and beyond became more feasible as scientists could receive and analyze data in real time. This continuous flow of information opened new frontiers for exploration and deepened our understanding of the universe. In the realm of fiction, the possibilities of quantum communication were explored in countless stories and narratives. Writers and filmmakers envisioned a future where humanity, connected through an unbreakable web of quantum networks, reached for the stars. These tales of adventure and discovery, though fictional, were grounded in the real advancements being made in quantum communication technology. As the decades passed, the integration of quantum communication into space exploration became more sophisticated. New colonies were established on the moons of Jupiter and Saturn, each connected to the others through a vast quantum network. The once insurmountable distances of space were bridged by instantaneous communication, fostering a sense of unity and collaboration among the far-flung human outposts. Back on Earth, the impact of quantum communication was equally profound. The same technology that connected distant planets revolutionized global communication networks. Governments, corporations, and individuals all benefited from the unprecedented security and speed of quantum communication. The world became more interconnected than ever before, with information flowing freely and securely across the globe. In conclusion, the potential applications of quantum communication, particularly through quantum key distribution, have far-reaching implications for secure communication, deep space networks, and space exploration. This technology has the power to transform our approach to exploring and colonizing the cosmos, ensuring that humanity's journey into the final frontier is both safe and successful. The seamless integration of quantum communication into every aspect of space exploration will pave the way for a new era of discovery and cooperation, uniting humanity in its quest to reach for the stars. In the quiet hum of a cutting-edge quantum research lab nestled deep within a sprawling, subterranean complex, scientists grapple with the mysteries of quantum entanglement. Entanglement, a phenomenon where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of distance, holds the promise of revolutionizing communication, computation, and our understanding of the universe itself. Yet, this seemingly magical interaction is fraught with complex technological and practical challenges that challenge the very limits of human ingenuity. Picture a vast network of quantum communication satellites encircling the Earth, each interconnected through entangled particles, forming a global quantum network. The vision is tantalizing: secure communication, unprecedented computational power, and a deeper understanding of the cosmos. But maintaining entanglement over such long distances poses a formidable technical challenge. As entangled particles are separated, their delicate quantum states become increasingly susceptible to disturbances. The transmission of these particles through space or even through fiber optic cables is fraught with difficulty. Photons, the particles often used to transmit quantum information, can become absorbed or scattered by the medium they travel through, leading to loss of information and weakening of entanglement. In this labyrinth of technological hurdles, researchers have turned to the realm of quantum repeaters devices, designed to extend the range of entangled particles by creating intermediate nodes that relay quantum information. Yet, the current technology is still in its infancy. Building and integrating these repeaters with sufficient fidelity to maintain entanglement over thousands of kilometers remains a monumental task. The technology must overcome significant challenges in synchronization and error correction to ensure that the quantum information remains intact as it traverses the network. At the heart of these challenges lies the issue of decoherence. Decoherence occurs when quantum systems interact with their external environment, causing the delicate quantum states to lose their coherence and collapse into classical states. This process is akin to a once clear melody being drowned out by the cacophony of an ever-changing environment. Decoherence is a persistent problem in maintaining entangled states, as even the slightest interaction with the environment can lead to the loss of quantum information. To combat this, researchers are exploring various strategies, such as isolating quantum systems in ultra-cold environments or employing error correction codes to counteract the effects of decoherence. However, these approaches come with their own set of challenges, including the complexity of maintaining near absolute zero temperatures and the computational overhead of error correction. Imagine a future where quantum computers, harnessing the power of entanglement, solve problems that are currently intractable. The vision is of a machine capable of performing complex simulations, optimizing supply chains, or even unraveling the secrets of fundamental physics. Yet, the practical implementation of such quantum computers faces significant hurdles. One of the primary challenges is maintaining quantum coherence within these machines. Quantum bits, or qubits, are the building blocks of quantum computation, but they are highly susceptible to interference. To build a reliable quantum computer, researchers must develop qubits that can maintain their quantum state long enough to perform computations, a task that remains exceedingly difficult given the current limitations of material science and technology. Moreover, the practical application of quantum technologies is constrained by the current limitations of scalability. Creating and managing large-scale quantum systems requires advancements in fabrication techniques, error correction, and system integration. As researchers push the boundaries of what is possible, they must address the issues of error rates and gate fidelities that plague current quantum processors. These challenges are not just technical, but also deeply intertwined with our understanding of quantum mechanics itself. As scientists delve deeper into the quantum realm, they must grapple with the fundamental nature of reality and the limits of our technological capabilities. In a distant future, where humanity has harnessed the full potential of quantum technologies, we might envision a new era of exploration and discovery. Perhaps quantum entanglement could be used to unlock the secrets of distant galaxies or to communicate instantaneously across the vast reaches of space. Yet, even in this future, the challenges of maintaining entanglement and combating decoherence will remain. The path to such a future is paved with incremental advancements and breakthroughs, each addressing the limitations of current technologies while pushing the boundaries of what is possible. The journey to overcoming these technological and practical challenges is one of relentless curiosity and perseverance. Researchers and engineers work tirelessly, often in the face of seemingly insurmountable obstacles, driven by the promise of a deeper understanding of the universe and the potential to revolutionize our world. As we continue to explore the frontiers of quantum technology, each challenge met and each breakthrough achieved brings us one step closer to realizing the extraordinary potential of entanglement and quantum communication. In the end, the quest to master the complexities of quantum entanglement and decoherence is more than just a technological endeavor, it is a testament to human ingenuity and our unyielding desire to understand the fabric of reality itself. As we stand on the brink of a new era in quantum science, the challenges we face today will shape the discoveries of tomorrow, guiding us toward a future where the mysteries of the quantum realm are no longer beyond our grasp, but are instead woven into the very tapestry of our technological and scientific advancements. Quantum communication, a field on the cutting edge of modern science, promises not only to revolutionize technology, but also to provoke profound ethical and philosophical inquiries. Imagine a world where our conversations, whether personal or state secrets, could be transmitted with absolute security. This is not the stuff of distant science fiction, but an emerging reality grounded in the principles of quantum mechanics. As researchers push the boundaries of what quantum communication can achieve, they also grapple with the broader implications for privacy and security, as well as the fundamental nature of reality and information itself. In a not-so-distant future, quantum communication networks might span across continents, rendering traditional forms of eavesdropping obsolete. The unique property of quantum entanglement, where particles remain interconnected across vast distances, ensures that any attempt to intercept the communication alters the quantum state itself, alerting both the sender and the receiver of potential tampering. This ability to detect eavesdropping with certainty promises an unprecedented level of privacy and security, but it also raises crucial questions about the nature of information control. If information is safeguarded so rigorously, what are the implications for individual privacy? How will this technology affect personal freedom, as well as governmental and corporate surveillance capabilities? Imagine a scenario where the privacy of personal communications is no longer a matter of technological robustness, but of ethical governance. Governments might wield quantum communication technology to ensure that their operations remain secure, but this could also result in a new kind of digital divide. While a select few have access to the most secure communication channels, the majority could find themselves subject to less secure, more vulnerable forms of communication. The disparity between those who can afford such technologies and those who cannot might widen, creating a landscape where privacy and security become privileges of the wealthy and powerful. Moreover, quantum communication could also prompt a re-evaluation of data ownership. With the potential for near-instantaneous and perfectly secure information transfer, questions emerge about who truly controls data. In a world where quantum networks can ensure the integrity and confidentiality of information, who should be entrusted with such power? The very concept of data ownership might need redefinition, as the line between personal and state secrets blurs. On a philosophical level, quantum communication challenges our understanding of reality and information transfer. Quantum entanglement, which allows particles to be linked in such a way that the state of one instantaneously affects the state of another, regardless of distance, defies classical notions of space and time. This phenomenon suggests that information can transcend the traditional boundaries of our physical world, raising questions about the fundamental nature of reality. If information can be transmitted instantaneously and securely, what does this say about the nature of time and causality? Does this mean that our conventional understanding of the universe is incomplete, or does it simply highlight the limitations of classical physics? In fiction, one might imagine a world where quantum communication has advanced to the point of creating a network that not only secures, but also reshapes reality itself. Consider a society where quantum networks can transmit not just information, but also influence physical states. People could communicate with each other in ways that blur the line between thought and action, leading to a new kind of interconnectedness, where privacy is both preserved and continuously negotiated. In this world, the ethical boundaries of information exchange would be constantly in flux, as individuals and institutions navigate the implications of such profound technological power. The philosophical implications of quantum communication extend beyond practical concerns about privacy and security. They touch on deeper questions about the nature of knowledge and reality. If information can be transferred instantly and securely, does this mean that our understanding of reality is fundamentally flawed? Could the instantaneity of quantum communication suggest that reality itself is not as fixed as we perceive it? This notion might lead to a re-evaluation of the role of consciousness in shaping our understanding of the universe. If quantum entanglement allows for instantaneous communication across distances, could our perception of time and space be fundamentally altered? In contemplating these questions, one might also ponder the ethical considerations of wielding such transformative technology. As quantum communication becomes more advanced, how will society balance the potential benefits with the risks? The capacity for absolute privacy could empower individuals and organizations to act with greater freedom, but it also raises the possibility of misuse. The ethical framework for quantum communication will need to address not only how information is protected, but also how it is used and controlled. The power to communicate securely might come with the responsibility to ensure that this power is used for the greater good, rather than for the benefit of a privileged few. Ultimately, the advent of quantum communication will likely prompt a re-evaluation of many fundamental aspects of our world, from the nature of privacy and data ownership to the very fabric of reality itself. As we stand on the brink of this technological revolution, it is essential to consider not only the immediate practical implications, but also the broader ethical and philosophical questions that it raises. The way we address these questions will shape the future of quantum communication and its impact on society, revealing not only what we can achieve with this technology, but also what it means to be human in an increasingly interconnected world. In the twilight of the 21st century, as humanity teeters on the edge of a new epoch in technology and knowledge, quantum communication stands as a beacon of transformation, promising to redefine the very fabric of our digital universe. The journey into the heart of quantum communication has been one of both profound discovery and intense speculation. Over the past decades, researchers have made remarkable strides in harnessing the peculiar properties of quantum mechanics to revolutionize the way we transmit and secure information. Yet, as we look towards the horizon of the next decade, the possibilities for this field seem as boundless as the cosmos itself, hinting at potential breakthroughs that could reshape our understanding of reality. Quantum communication relies on the enigmatic principles of quantum entanglement and superposition. These phenomena, first theorized in the early 20th century, have been experimentally validated to an astonishing degree, providing a foundation upon which the future of secure and instantaneous communication is being built. The cornerstone of this new era is quantum key distribution, QKD, a technique that allows two parties to share a secret key with absolute security, impervious to eavesdropping. As we stand on the brink of widespread QKD deployment, researchers are exploring ways to overcome existing limitations, such as distance constraints and the need for specialized equipment. Ongoing projects aim to develop satellite-based QKD systems, enabling global secure communication networks that span continents and oceans. In the realm of fiction, imagine a world where quantum communication has evolved beyond our wildest dreams. Picture a global network of quantum satellites, their shimmering light threads connecting every corner of the Earth. These satellites, floating serenely in the void of space, relay encrypted messages instantaneously, enabling real-time communication with absolute privacy. In this envisioned future, hackers and spies have become relics of the past, their attempts to breach quantum networks as futile as trying to catch stardust with a net. As humanity explores further into the cosmos, quantum communication systems could establish secure links between distant space colonies and Earth, facilitating the exchange of information across light years without fear of interception. The quest for advancements in quantum communication is not without its challenges. Current quantum communication systems are hampered by issues such as signal loss over long distances and the delicate nature of quantum states, which can be easily disrupted. Researchers are diligently working on developing quantum repeaters, devices that could amplify and regenerate quantum signals over vast distances, thus paving the way for truly global quantum networks. These repeaters would act like relay stations, ensuring that quantum information can traverse the Earth and beyond without degradation. Additionally, there is an ongoing effort to integrate quantum communication with existing classical communication infrastructures, creating hybrid systems that leverage the strengths of both technologies. In the next decade, we might witness the dawn of a new era in which quantum communication becomes ubiquitous. One can envision a future where everyday devices, from smartphones to smart appliances, are equipped with quantum communication capabilities. This would not only enhance the security of personal data, but also enable a new level of interconnectivity, where every device in a smart city communicates seamlessly with others, all while maintaining the highest standards of privacy and security. The advent of quantum networks could lead to the development of quantum internet, a vast and intricate web of quantum entangled nodes, where information is transmitted not as bits, but as quantum states, fundamentally altering the nature of data exchange. Predictions for the coming decade also hint at the convergence of quantum communication with other cutting-edge technologies. Quantum computing, with its potential to solve problems currently deemed intractable, could be tightly integrated with quantum communication systems. Such integration could lead to unprecedented advances in fields ranging from cryptography to complex simulations, enabling researchers to tackle challenges that are currently beyond our grasp. The synergy between quantum communication and quantum computing might also give rise to novel applications, such as quantum-enhanced artificial intelligence, where machine learning algorithms benefit from the superior processing power of quantum computers. Amidst the excitement, there are also speculative visions of future breakthroughs that stretch the boundaries of our imagination. Consider a scenario where quantum communication enables the establishment of a quantum web across the galaxy. In this speculative future, interstellar civilizations might communicate using advanced quantum networks that span light years, exchanging knowledge and collaborating on cosmic projects with a level of security and efficiency previously thought impossible. The potential for quantum communication to facilitate communication with extraterrestrial intelligence, if it exists, adds another layer of intrigue to the field. As we push the limits of technology and explore the universe, quantum communication could play a pivotal role in bridging the vast distances between worlds and fostering connections that transcend the confines of our planet. As we stand on the threshold of this exciting future, the research and development in quantum communication continue to unfold with breathtaking speed. Each breakthrough, each discovery, brings us closer to realizing the full potential of this transformative technology. The journey is one of constant evolution, where the line between science and science fiction blurs, and the dreams of today become the realities of tomorrow. The next decade promises to be a period of profound transformation, where quantum communication not only enhances our digital infrastructure, but also shapes the very way we perceive and interact with the world around us. As we venture into this new era, the echoes of our current efforts will resonate through the corridors of time, marking the beginning of a new chapter in the story of human progress. Quantum entanglement is a phenomenon that challenges our classical understanding of the universe. At its core, it describes a scenario where two or more particles become interconnected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This strange connection was first highlighted in the 1930s through the Einstein-Podolsky-Rosen (EPR) paradox, which questioned whether quantum mechanics could fully account for the physical reality of particles. The EPR paradox suggested that if quantum mechanics were complete, it would imply spooky action at a distance, a concept that Einstein found troubling. Later, John Bell formulated Bell's theorem, which provided a way to test these notions experimentally, showing that entangled particles could indeed exhibit correlations that defied classical explanations. These theoretical foundations paved the way for numerous experimental verifications of entanglement. Understanding how particles become entangled involves delving into the principles of quantum mechanics. Entanglement occurs when particles interact in such a way that their individual quantum states cannot be described independently of each other. This is closely tied to the principle of superposition, where particles exist in a blend of all possible states until measured. Upon measurement, the wave function collapses to a definite state, revealing the entangled nature of the particles. One of the most famous experiments demonstrating this phenomenon is Alain Aspect's 1980s experiments, which confirmed that entangled particles display correlations consistent with quantum mechanics and not classical physics. The implications of quantum entanglement extend into the realm of communication, introducing the concept of quantum communication. Unlike classical methods, which rely on sending signals through physical media, quantum communication utilizes the properties of entangled particles to transmit information. Quantum teleportation is a notable application of this, allowing for the transfer of quantum states between distant locations. This process, however, is distinct from the science fiction notion of teleportation, as it does not involve the physical transport of matter, but rather the transfer of quantum information. Space communication, with its inherent challenges, stands to benefit significantly from quantum entanglement. Current methods face issues such as signal delay and data loss due to the vast distances and interference encountered in space. Quantum entanglement offers potential solutions to these problems, enabling instant communication across great distances by leveraging the interconnectedness of entangled particles. This could revolutionize how we manage and transmit data in space missions and explorations. Recent advancements in quantum satellites highlight the practical progress in this field. China's Milestones satellite, launched in 2016, represents a milestone in demonstrating quantum communication capabilities from space. Through real-world experiments conducted with this satellite, researchers have successfully tested quantum key distribution (QKD) and other protocols that could reshape how we approach secure and efficient space communication. The potential applications of quantum entanglement are vast. Quantum key distribution promises a new level of security for communication by ensuring that any eavesdropping attempt alters the quantum state, thus alerting the communicating parties to potential breaches. Additionally, entanglement could enhance deep space communication networks, making it feasible to maintain robust communication with distant spacecraft and missions. This, in turn, could have significant impacts on space exploration and colonization efforts, facilitating more reliable interactions with far-reaching missions. However, there are significant technological and practical challenges to overcome. Maintaining entanglement over long distances is fraught with difficulty due to factors like decoherence, where environmental interactions disrupt the delicate quantum states. The current limitations include the need for better technology to preserve entanglement and more sophisticated methods to mitigate environmental impacts. Future research is focused on addressing these issues, with ongoing efforts aimed at improving the robustness of quantum systems and extending their practical applications. Beyond the technical aspects, quantum communication raises ethical and philosophical considerations. The potential for quantum technology to impact privacy and security is profound, as it offers unprecedented levels of secure communication, but also necessitates new frameworks for handling such power. Philosophically, quantum entanglement challenges our understanding of reality and information transfer, provoking questions about the nature of connection and causality in the universe. Looking ahead, the field of quantum communication is rapidly evolving. Ongoing research and future projects are set to explore new frontiers in this technology, with predictions of groundbreaking advancements over the next decade. As our understanding deepens and technology progresses, quantum communication could reshape how we perceive and interact with information across the cosmos, heralding a new era in our exploration of space and beyond.